Hi, welcome to this video. In this video I'm going to explain how I created the self-driving Robot Wagon, which is programmed with the YAL programming language. So what will be the contents of this video? First, why I did this project. Then something about the ultrasonic distance measurement module that I'm using for measuring the distances. Some of the design choices I made by doing this project. A little bit information about multiplexing sensors and why that was needed. Then a schematic diagram which shows the hardware and a breadboard on which I built all the electronics. I will explain at a high level the control algorithm that I'm using. Then something about the software which was created, some pictures, of course a demonstration video showing the device in action, and at the end of this presentation you can find some references. So why did I do this project? It was just for fun. I just wanted to make a self-driving robot wagon. I'm using a PIC microcontroller and I'm also using 3 ultrasonic distance measurement modules for measuring distances. It is programmed with the YAL programming language. So something about this ultrasonic distance measurement module. It looks like this, and it uses ultrasonic sound to measure the distance. For that you can start it by activating a trigger pulse of at least 10 microseconds, and then the software has to measure the echo signal that is returned by this module. And the length of the echo signal determines the distance. And the range of the module is between 2 cm and 400 cm, which is quite large. And it's important for this project to use a version that operates at 3.3 volts, because older versions of this module only work at 5 volts. So what does it look like? So I have an example of a pulse and echo signal in a range of 20 centimeters, so an object in 20 centimeters in front of the module. The yellow line is the pulse signal and the blue line is the echo signal, and the length of the echo signal determines the distance. For example, if you look at 30 centimeters, you see this, the trigger pulse is the same, but the echo signal is longer. And by measuring the length you can then determine the distance. So what are the design choices that I made? First, of course, you need a kit. And I'm using a kit with 2 DC motors. I'm also using 3 distance sensors, but because I'm using 3 I need to multiplex them, but I will explain that later. And these motors operate at 6 volts, but 6 volt is too much for the electronics, so I'm also using a voltage regulator at 3.3 volts. And I wanted to use rechargeable batteries, but when you buy this kit it has a battery holder for 4 batteries, but that's not sufficient if you're using rechargeable batteries. So I replaced it by a battery holder that can hold 5 AAA batteries. And I'm also using pulse width modulation to control the speed of the motors, since these motors are DC motors, and the way to control the speed is by using pulse width modulation. So something about multiplexing sensors. Why is that needed? I'm using a YAL library for this module to measure the distance, but this YAL library only supports 1 module. That means it uses 1 trigger pin and 1 echo pin, and it also uses 1 timer of the PIC microcontroller. So I have 3 sensors, so we need to multiplex them. Now for that I'm using a 74HC4052, which is an analog multiplexer. So each time the PIC will trigger 1 sensor, measure 1 sensor, then trigger the next sensor and measure the sensor. And this a multiplexer is an analog multiplexer, but it works quite well. I could also have done it with electronics, with gates, ANDs and OR gates, but it would make the circuit much more complex. So this is the simplest way to multiplex the signals. So then the schematic diagram. It consists of 2 parts, the controller part and the multiplexer and the motor part on the left. So it starts with, of course, in the microcontroller, which does all the smart things. Then it controls the multiplexer for sending the trigger signal and returning the echo signal. And on the right you have the 3 sensors. As I mentioned before, I need a different voltage for the electronics, because otherwise the voltage will be too high, so it all operates at 3.3 volts. And also important is this capacitor, because each time you switch on the motor it draws quite some current, and this capacitor will smooth the current out. Then we have the second part, which is the motor control. And this is called an H-bridge. And normally you can of course buy an H-bridge module, which can let's say draw or support a lot of current, but I don't need that. So I made it with transistors. So how does it work? When the PIC activates, for example, the left forward signal, these 2 transistors will be activated, which means that the current flows in this direction through the motor. If the PIC would trigger the left reverse signal, then these 2 transistors will be activated and the current will be in the opposite direction, so it will be reverse. Of course the PIC will never activate both signals at the same time, because then you would make a short circuit. So I built this electronics on a breadboard, which fits nicely on this whole chassis. And you can see all the connections. So you have the battery connections, you have the connections for the sensor, so the trigger pulses, the echo and the power, and you have the motor connections. Then the control algorithm at a high level. So what the PIC does, it measures first all the distances of all the sensors. Then if the distance on the left or the right side of the wagon is less than 20 centimeters, then one motor is stopped and the other one is started. And this will result in making a hard turn. If the distance is more than 20 centimeters but less than 30, then it will increase the speed of one motor and decrease the speed of the other motor. Then that will result in a soft turn. But if the distance is less than 20 centimeters in front of the wagon, then both motors are put in reverse. And in all other cases, both motors are put in the forward direction. So the software, what does it do? Of course, it implements the algorithm I just explained, and I'm using one PIC microcontroller, and the flash and the ROM is sufficient to fit in this PIC. You can even extend the algorithm because there's still some room left. And as I mentioned before, the main loop continuously measures all the sensors and continuously controls the motors. And I'm using pulse width modulation, but this pulse width modulation is for controlling the speed, and it's done in software. The PIC also has pulse width modulation hardware on board, but it only has it for one motor, and I of course have to control 2 motors, so that's why it's done in software. And as I mentioned before, the YAL library is used for measuring the distance, and by multiplexing I can use more sensors at the same time. Okay, so what does the device look like? So this is the front view. I also added some LEDs in the front just for fun. And this is the top view. And there you can also see the battery holder holding 5 rechargeable batteries. So the next demonstration video will show the device in action. If you want to know more about this project, you can visit my GitHub account and download the software and the hardware and the schematic diagrams. If you want to know more about YAL, you can visit the YAL website. If you have questions on how to use YAL, there's a very good YALib tutorial that you can download from the website, or there's a YAList Google group where you can post your questions. If you find bugs or maybe have special requests, there's a YALib Google group. And you can find all the YAL sources, which is open source, on GitHub too. I hope you liked this video, and thanks for watching.